I have here a magnesium bar, and the magnesium bar has a length L, and I can calculate the speed of sound for magnesium by taking its Young's modulus, which is there, divided by rho, which is there, and I come up with a speed of sound which is about 5 kilometers per second. If you look at those numbers, they're all substantially higher than the speed of sound in air, which is only some 340 meters per second. So the speed of sound for magnesium is some 15 times larger than the speed of sound in air. If this bar has a length L, this pressure disturbance will start to move to the left, and then it will come back here. So it will have made a complete journey, which I call the period. It has made a complete journey in so many seconds to L divided by the speed of sound. And so the frequency of this bar, the frequency at which it would like to oscillate when I give it a bang, is 1 over t, and that is the speed of sound divided by 2L. Now, for those of you who will take 803 in the future, you will see a much better derivation of this frequency. So this is a poor man's version. The speed of sound is about 5 kilometers per second. The length of the bar is about 122 centimeters. And so that translates into a frequency of roughly 2100 hertz. So the frequency for this magnesium bar is about 2100 hertz. And you can hear that. It's a beautiful tone. I hold it here, and I will bang it here. Can you hear it? No? Can you hear it? 2100 hertz, beautiful tone.